Alright, so this is exam 3 review. Alright, the one that you did. Let's look at the concept that were tested. So question 1. Which of the following alcohols is the least acidic? Now, the best way to look at it is to find the conjugate base. What do I mean by conjugate base? Find the most acidic hydrogen, which happens to be this hydrogen. So if this base, which would be OH minus, let's just use B minus as a prototype, takes out the acidic hydrogen. That's acidic because it's bound directly to an electronegative group oxygen. So when that reaction happens, look what you get. You get O negative, right? The oxygen has much electron density there, but lucky enough, we have an electron drawing group which can pull out the electrons from the oxygen by inductive effect. That stabilizes the conjugate base, and so this one is a very, in fact, out of them, that's gonna be the weakest conjugate base, which means this one is the strongest acid out of the set, because the conjugate base is stabilized both by inductive effect and resonance. The electrons are pulled out of the negative oxygen. Of course, the base accepts the hydrogen, you get BH. So if this is OH minus, your BH would be H2O. So the answer is not A. A is the most acidic because you have an electron drawing group. So you can tell now what the answer is, because the second one, if you look at the second one, you have two OHs, right? So if this hydrogen is lost to a base and you get O minus, guess what happens? You have an OH here. The oxygen has a lone pair. So instead of the OH withdrawing these excess electrons from the oxygen, it's actually giving it more. So this turns out to be a stronger conjugate base out of what we have, which means it came from the weakest acid. Okay, so strong conjugate bases come from weak acids. Weak conjugate bases come from strong acids. So the answer is B. Now, H and the method don't do much of the donation compared to OH, because OH is donating by resonance, like I showed you here. There is resonance donation. Here there was electron withdrawing, so that stabilizes the conjugate base. This is not stabilizing the conjugate base, it's making it even more basic because you're donating electrons by resonance. So the answer is B. Cannot be C or D, because OH donates by resonance, hydrogen by inductive effects. The method donates by inductive effect. Donation by resonance wins, which means you get the strongest conjugate base that came from the weakest acid of the set. Let's look at question 3. Arrange the following structures from the one with the least boiling point to the one with higher boiling point. So here you're looking at intermolecular forces. So the more the hydrogen bonding you get, the higher the boiling point, because hydrogen bonding is stronger than dipole-dipole. Okay, so the first one, I don't see any hydrogen bonded directly to an oxygen. So if I bring two molecules of these together, all I'm gonna get is dipole-dipole, because the oxygen is partially negative, which means the carbons are partially positive. So you'll expect there's gonna be some attraction here, and that's gonna be dipole-dipole. Okay, so the one from the one with the least boiling point, A is the one with the least boiling point, and then followed by C, because there's only one OH, followed by B. B has two OHs, so you can imagine it's gonna have the opportunity to make so many hydrogen bonding from here to one hydrogen which is bonded to an oxygen of another molecule, or from here to a hydrogen right? You get another hydrogen bonding here, also here. So the more the hydrogen bonding you get, the more intermolecular hydrogen bonding you get, the stronger the binding of the two molecules, and then the higher the boiling point. So arrange the following structures from the one with the least boiling point to the one the highest. B will have the highest, so the answer is B for that one. Now let's do question 4. What does it say? Which of the following structures is the most soluble? Again, the one that can do more hydrogen bonding is the one which is more soluble. The answer is B. And then let's go to the next one. What is the UPAC name for that structure? So let me do question 5 on here. So since you have a chair, okay, you have a chair, and I see that this one is up and this is down, so they are in trans configuration. If I were to draw the ring, I'll get it like this. Actually it's the other way around, because OH is up, so it gets the shaded wedge. CH3 is down, so it gets the dash. Okay, so it's trans. So this ring can just be drawn like that. This is 3D, and that is the perspective, 2D perspective. Okay, so it's trans to begin with, so it cannot be cis. It cannot be ortho because this is not a benzene ring. Methyl cyclohexanol is wrong because you've not specified the position of the methyl group. So one would start from the OH, then the methyl is on carbon 2, so it's 2-methyl cyclohexanol. But that's not it. You also have trans. So answer A. Which of the pairs in the choices below cannot hydrogen bond? Okay, so for the pairs to bond, you have to have both of them having some OHs or NHs. Okay, so there's no OH here. That's an ether, and that's an ether. So no hydrogen bonding possible for that set. This is an alkane. It's not polar. This is an ether. There's no OHs on there. Okay, in fact, if you were to draw this molecule right here on B, you'll get a double bond to an oxygen to a double bond. That's how it looks like. That's an ether. This molecule here looks like this. There's a double bond in there because of CH2 and H. So that one cannot hydrogen bond. These two can hydrogen bond because I see an OH there and an OH there. And then these are all nonpolar. So this one cannot hydrogen bond. So those were the three choices. The hydroxy group is a good leaving group. No, it's not, because let's say you have this is question 7. Let's say you have an OH and you lose it. What will you get? Or you'll get a carbocation, alright, but you'll also get OH minus. So is OH minus a good leaving group? No, because this is a strong base. Good leaving groups must form weak bases. So the answer is false. Which of the following will react slowest with HCl? Pull it up. So if you're reacting with HCl, you're thinking SN1. Alcohols react with acids in SN1 fashion. If it's SN1, you have to think of formation of carbocation, which is the rate determining step. So which of these will form the most stable carbocation? Now, for the structure A, if you have to lose the OH, OH is a poor leaving group, so you'll have to take advantage of the acid to protonate the OH so that it can leave as water and not OH minus, because we just said OH minus is a poor leaving group. So once you have this can leave, okay, then you get a carbocation. That carbocation is primary. Remember, for SN1, prefers secondary over prefers tertiary over secondary over primary over methyl carbocation. So we are looking for the one that will react slowest. That's a primary. Okay, for B, if the OH falls off, if the OH falls off as water following the same mechanism, like here we lost it as water, you get a secondary carbocation. The carbon bearing the plus charge is bonded to two other carbons, so it's secondary. Here the carbon bearing the plus charge is bonded to one carbon, so it's primary. So that one is not the answer. So let's go fourth. So the next one, once the OH falls off as water, you get a tertiary carbocation. The carbon bearing the plus charge is bonded to three other carbons. And then lastly, you have methanol. When the OH falls off, you get CH3 plus. That's a methyl carbocation. And according to our ranking for SN2, the methyl carbocation is the least reactive. So structure D will react the slowest because the carbocation is the least stabilized by inductive effect. You see, like tertiary, the plus charge will be neutralized by electrons through bond because it has the most R groups around the C+. Which of the following cannot be oxidized by PCC or Jones? I'm gonna need to create space. Let's see. Okay, so the point that we said about oxidation of alcohols is, if you want to oxidize an alcohol, the carbon bearing the OH must have a hydrogen. So A can be oxidized by PCC to its aldehyde, because PCC is mild. The same A can be oxidized by Jones reagent, which, remember, it's chromic oxide in presence of sulfuric acid. Okay, let me write it again so you can read. CrO3 in presence of sulfuric acid. That's a strong oxidizing agent. It oxidizes the primary alcohol to an aldehyde, but does not stop there. It goes all the way to the carboxylic acid. So A can be oxidized by both. B can be oxidized by either PCC or Jones. Both of them will give you a ketone, because secondary alcohols, this was primary, secondary alcohols are always oxidized to the ketone, whether you have PCC or Jones, which is chromium oxide sulfuric acid combination. So that's not the answer. We are looking for one that cannot. Now C cannot be oxidized because it's a tertiary alcohol. Tertiary alcohols don't get oxidized. Reason being, let's see, where is my reason being? Here there is no alpha hydrogen. You see, here there's a hydrogen sharing the carbon with OH. That's why we can oxidize it, because oxidation is removal of hydrogens. If you can think of it that way, the hydrogen is removed on here. So you have to have at least one hydrogen sharing the same carbon as the OH for the alcohol to be oxidized. So that's why C cannot be oxidized, because it lacks the alpha hydrogen. Obviously D can be oxidized because there are three hydrogens on same carbon as OH. So the answer here is C. What is the major product of the reaction below? That's an SN1 reaction. Again, you're reacting an alcohol with an acid, so you think SN1. Okay, so is OH a good leaving group? The answer is no. So how do we make it a good leaving group? You protonate it with the acid so that it can now leave us water rather than leaving us OH minus, which is a strong base. So once that's protonated, now this can fall off as water in the S1 mechanism to make the carbocation, and it happens to be a tertiary carbocation. Only then will the Br, you see here, once you take out the hydrogen, the Br falls off, you get Br minus. So that Br minus will come back to attack that carbon and you get substitution. So overall, you're moving from the alcohol to the alkyl halide. The OH is replaced by Br, so it's a substitution. Unimolecular because you're going through carbocation. Nucleophilic because now Br minus here is a nucleophile. Substitution because you're substituting OH with Br. So the answer here should be structure A. What is the product of the reaction below? That's a secondary alcohol, so it should be oxidized to the ketone, which is C. What is the geometry of the carbon atom of a carbonyl? What's the molecular geometry of the carbon atom of a carbonyl? So that's a carbonyl. Okay. So if you have a carbonyl, most likely it's going to be bound to other elements, either carbon-carbon or carbon-oxygen or carbon-hydrogen. It doesn't matter. You have 1, 2, 3 electron domains. So the molecular geometry, 3 electron domains, so that will give you the electronic geometry. So the EG is trigonoplanar. That's what I should probably say. But again, because of the double bond, let me draw it again here because I explained EG instead of Mg. Because of the double bond, you expect around the carbon of the carbonyl is gonna be flat because there's a double bond on that carbon. That's how you know that it's planar. It has an element of planarity. But you're joining 3 elements, so it's trigonal. So it's trigonal planar. Molecular geometry, which happens to be the same as the electronic geometry because the central carbon does not have a lone pair, so it should be the same. What is the product formed when methyl magnesium chloride reacts with cyclopentanone followed by acidic workup with H3O+? If you remember, that's called Grignard reaction. That's Grignard reaction. So cyclopentanone looks like this. Is a 5-membered ring, which is a ketone, none. And then the Grignard CH3 MgCl reacts with it. And we said whenever you have this, just take the R group to be negatively charged. It's going to be used to attack the carbonyl. And this opens up. What do you get? You get O minus and the CH3, right? So it says followed by acidic workup. So acidic workup simply means that you are adding H plus. If you want, I can show you the mechanism using H3O plus. So the oxygen uses one of the 3 lone pairs to take out the extra hydrogen, neutralize the oxygen, so you end up with an alcohol. So that's what workup means, where you have O minus becomes OH. Okay, and then the metal is still there. That will be the final product. So whenever you do Grignard with ketones, you get to convert the ketone to tertiary alcohol. So the ketone is converted to a tertiary alcohol. So the name of this tertiary alcohol will be, okay, it's a cyclopentanol. We know that, but the methyl group happens to be on the same carbon, so it's 1-methyl cyclopentanol. That will be the product, which is this. All right. So let me clear up this page so I can use it for the next question. Grignard again, this time with an aldehyde called formaldehyde. So formaldehyde is an aldehyde with 2 hydrogens, and then you're reacting it with a Grignard, MgBr. So again, I will just take the R group and make it negatively charged. We use it as a nucleophile. You are attacking the carbonyl of formaldehyde. That's your formaldehyde, what you use in the zoology lab to preserve animal material. So you attack the carbon, the pi bond opens up, so you get O minus. Here you had 2 lone pairs. After donating the pi bond that opened up, you're gonna have 3 lone pairs. The hydrogens are still there, and the methyl is added. Okay. So now, usually we follow it with acid workup like we did before. So the O minus becomes OH. It's just a presumption that we always assume. You should know that we always follow with acid workup like we did in the previous question. So if I was to assume the hydrogens on the carbons, this would be the structure. That happens to be ethanol, and it's a primary alcohol. The carbon bearing the OH is bonded to one other carbon, so it's primary alcohol that results. How many alpha hydrogens are in the carbon in the structure below? So for question 15, I see you have a ketone. Alpha carbon is a carbon next to the carbonyl. So you would just show the hydrogens implied, and you will know that you will have 3 alpha hydrogens on that structure, and I've drawn them there in red. So the answer is 3 alpha hydrogens bonded to the alpha carbons. Like I said, alpha carbons are carbons bonded directly to the carbonyl. You learned that in the chapter of ketones. Which of the following cannot form an enolate? Now, I hope you remember what enolates are. If you have an alpha hydrogen, just to give you an overview, if you have an alpha hydrogen, I'm just showing one of those, there are 3 here, 3 here, and you bring a base. If you take out the hydrogen, the electrons go there. Okay, the base here could be OH minus or CH3 minus. Let me say OR minus. So you will have CH2 with negative charge. Remember here there is 2 hydrogens. There were 3 hydrogens once taken out by the base. Of course, the base makes the conjugate acid. So this is called a carbanion because you have a negative charge on a carbon, which can do resonances. Once it does resonances, what do you get? You get an enolate because the double bond will be right there. This is called the enolate. So the enolate form can resonate to the carbanion form. So you must have alpha hydrogens for you to make enolate. So let's see who cannot form enolates, who doesn't have alpha hydrogens. Obviously the answer is B, because if you look at the first one, you have alpha hydrogens. They are not here. Here there's no alpha hydrogens, but right here you have them. So these hydrogens can be pulled out. Those are alpha. Okay. So A is out. A can form an enolate. We are looking for one that cannot form an enolate. B. Here there is no alpha hydrogen. Here there is no alpha hydrogen. How do I know that? We already have 4 bonds. So the answer is B. C is what I've done. And then D, ethanol, has alpha hydrogens right here. So that can form an enolate. What is the UPAC name of the structure below? Let's move both pages down. Okay, so the structure looks like this. It seems to be a ketone, so the suffix name should be ONE. Okay, so C is out, that's an aldehyde. Alright, so give the carbonyl the priority numbering, locant position. So it will be position 3. Identify the longest chain containing the carbonyl. So I have a methyl on 5 and 6. So the right name will be 5, 6. You have to say dimethyl because there are 2. And then hept because there's 7 carbons. But we have to specify the position of the carbonyl of the ketone, so we'll say 5,6 dimethyl 3, 3 meaning this 3 position of the carbonyl, because the carbonyl can dance along the longest chain and change positions. So 5,6 dimethyl 3, then heptanone, that would be the name. Okay, so you can also call it 5,6-dimethyl-heptane 3-on. It's the same thing. The ending here could be 3-heptanone, or you could say heptane, and then you put your 3 in just before the ONE, because the 3 defines the on, the ketone position, the carbonyl of the ketone position, the position of the carbonyl of the ketone. That's what the 3 defines. Which of the following is a hemiacetal? Now let me see. Hemiacetal. So we said hemi means half. So hemiacetal is simply half the acetal. And what's the acetal? When you have RO sharing a carbon, right? That's an acetal. But when you have HO and OR sharing a carbon, that's hemi, because you don't have the 2 OR, so it's half the acetal. So that's what we are looking for. What will be the answer for question 18? What's the answer for question 18? This A is an acetal, because I see I have an OCH3, that's an OR group, and I have the oxygen within the room, that's another R group. So here, looking at this carbon right there, I have OR and I have OR. Of course, I have a hydrogen on there and I have a carbon. So this carbon here is this carbon right there. So this one is an acetal, because it takes that general formula. So for B, B is a hemiacetal because this carbon right here is bonded to an OH and an OR group. Okay, this whole thing, the rest of the ring is OR group. So that's hemi because it looks similar to that. Of course, C is an alcohol and D is an ester. Which of the following is an acetate? I've already said A is an acetate, so we go with A. Ketones and aldehydes undergo addition reaction rather than substitution reactions. That's true, because what you do with ketones is just attack the carbonyls. So where there's a ketone, if you have a nucleophile, you simply attack the carbonyl and this opens up. You've added the nucleophile. Specifically, let's say you have OH minus reacting with acetone. Okay, so you use the lone pair to attack acetone, that opens up. You've added the OH onto the acetone. So it's an addition, not a substitution. Substitution might occur with acyl chloride and esters. So the ketones and other aldehydes undergo addition reaction rather than substitution. True. What is the intermediate product for the reaction below? What is the immediate product for the reaction below? Usually when you have, okay, let's see. When you have a hemiacetal, like you see in question 22, that's an hemiacetal. Okay. If you give the hemiacetal an alcohol, okay, I remember very well, I gave you the shortcut where the OH is gonna be lost, the H of the alcohol will be lost, and you're condensing the molecule together. So what you'll be left with is OET, and that's an acetal. So you can convert the hemiacetal to an acetal with loss of H2O, which is what's circled. So the immediate product here is gonna be answer B, because this one right here is ethanol, if you are not aware. Okay, what's the hemiacetal carbon in the structure below? It's gonna be carbon 3, because you have an OH and an R group. See, this R group, the rest of the group is considered R. So you have OH and OR group sharing the same carbon 3. So that's the hemiacetal carbon. Which of the following is the most acidic? Now here you're going to consider electron pool. The closer the electron withdrawing groups are to the oxygen to the right, the more acidic it is. So again, your concentration here on question number 24, your concentration is the stability of the conjugate anion. For example, let's look at the answer. The most acidic here should be C. The reason being, those fluorines are very close to the oxygen. So let's say that the acid reacts with the base. So let's say the base is OH minus, or you can use B minus. So if the base takes out the acidic hydrogen, what do you end up with? Your product will be F carbonyl O minus. You see, these fluorines are very close to the oxygen of the conjugate base, right? And the fluorines are known to be electron withdrawing, so they stabilize the conjugate base by what we call inductive effect. They are closest to the oxygen. Here, if you look at the rest, these fluorines are away from the oxygen. These ones are 1 carbon away. This is only 1. So the one that's most acidic is C, because that will give you R. Out of all, this will be the weakest conjugate base, which means it came from the strongest acid, not in the world, but the strongest acid of the 4 of them. If the carboxylic acid below is heated in ether in the presence of an catalyst of an acid, like sulfuric acid, what major product is expected? So this reaction, let's see if I can delete this. Come on. No. Okay, so question 25 is referring to a reaction we called Fischer esterification. And I gave you the shortcut where water will be lost. So let's review that. That's your acid reacting with your alcohol. So the OH of the acid will fall off, the H of the alcohol will be lost. So this is lost as water. Click the rest of the structure, you'll see how the product looks like. I need red. So the rest of the structure will be hanging bond to the rest of the alcohol, and that's an ester. The byproduct will definitely be the hydrogen and the OH, which is just water. So the major organic product is gonna be an ester, and the ester will be A, because OET. This part here is the ET, it's an ethyl. All right. And what's the UPAC name of the structure? Below. So let's see if I can scroll down. So we can do this. So we need the UPAC name of this. So we start by numbering the carbonyl of the acid 1, 2, 3, 4, and 5. So we have the methyl on carbon 4, so it's 4-methyl, and then it's 5 carbon, so it's pentanoic acid, 4-methyl pentanoic acid. Okay, so the answer is D. And then for 27, what's the reagent needed to convert this to this? Okay, so this is one of those reactions that you have to have flashcards to know that the reagent is thionyl chloride. We use thionyl chloride SOCl2 to convert. So if you have a carboxylic acid, you can use PCl5, you can use SOCl2 to convert the R to convert the OH to the Cl, to replace the OH here with a Cl to make what we call an acyl chloride. Okay, so that was it.